The de Havilland Mosquito defied every law of military logic, and yet it flew. In 1938, when Geoffrey de Havilland walked into the Air Ministry with his proposal, the response was entirely predictable. His vision, a bomber constructed almost entirely from timber, stripped of all defensive weaponry, depending solely on velocity for survival, struck military planners as absurd. This wasn't innovation. This was madness dressed up in blueprints. Metal represented the future of aviation. Everyone knew that. Wood, that belonged to the previous war, to fabric-covered biplanes and canvas-skinned fighters, not to an air force preparing for industrialized conflict against Adolf Hitler's Third Reich. The Air Ministry's rejection letter arrived swiftly, polite, professional, and utterly final. Yet de Havilland persisted. Within that stubborn refusal to accept defeat lay the seed of one of the war's most elegant and effective aircraft. And unexpectedly, it would create the perfect opportunity for an unlikely hero to make it even faster. Here's the crisis Britain faced in the late 1930s. The nation confronted a grim arithmetic problem that kept military planners awake at night. Rearmament was accelerating frantically as war clouds gathered over Europe. But aluminum, the essential material for modern aircraft construction, was desperately scarce. Every military branch competed viciously for limited supplies. Fighter production demanded it. Bomber construction consumed it. The supply chains couldn't possibly satisfy the explosive demand. Resources were rationed, fought over, allocated and reallocated in endless bureaucratic battles. De Havilland's genius lay in recognizing what others perceived only as a crippling limitation. His company had invested decades perfecting laminated wood construction techniques, developing sophisticated methods for bonding birch plywood with lightweight Ecuadorian balsa and robust Canadian spruce, using specialized casein glues originally developed for high-end furniture manufacturing. These advanced techniques produced structures that were simultaneously lightweight and remarkably strong. But here's where de Havilland's insight became revolutionary. These components could be manufactured by craftsmen who'd spent their careers building furniture and pianos, skilled tradesmen who were completely locked out of metal airframe production. The Mosquito wouldn't compete with Spitfire production for precious aluminum. It would tap into an entirely separate pool of manufacturing capacity. A war machine assembled by peacetime craftsmen. A bomber that didn't steal resources from fighter production. It was elegant problem-solving disguised as an aircraft design. The design that crystallized in 1939 was audacious in its simplicity. Twin Rolls-Royce Merlin engines, the identical power plants propelling Hurricanes and Spitfires through combat, mounted on a sleek, aerodynamically refined fuselage with a wingspan of 16.5 meters. No, gun turrets consuming weight and creating drag. No separate bomb aimer's compartment adding complexity. Just a pilot and navigator crammed into a tight cockpit, wagering their lives on mathematical calculations and aerodynamic efficiency. The performance estimates promised something genuinely extraordinary. A maximum speed exceeding 400 miles per hour at operational altitude, faster than virtually any fighter aircraft then in operational service worldwide. In this radical design philosophy, speed replaced armor plating. Velocity became both defensive shield and offensive weapon. The concept was simple. Don't get hit by making yourself impossible to catch. When the first prototype, conspicuously painted training yellow for visibility, lifted off from Hatfield Aerodrome on November 25, 1940, test pilot Geoffrey de Havilland, Jr. experienced something unexpected. The aircraft didn't merely fly competently. It felt eager, responsive, almost enthusiastic. The controls responded crisply. The engines delivered power smoothly. The aircraft seemed to want to fly fast. By February 1941, official evaluation trials at Boscombe Down confirmed that these weren't merely optimistic projections or wishful thinking. At 22,000 feet, the prototype touched 392 miles per hour. And critically, this was still a prototype. heavy with testing instrumentation, powered by engines not yet optimized for production specifications. The Air Ministry's initial skepticism began crumbling like chalk cliffs in a storm. But here's the critical distinction that every combat pilot understands. Theoretical speed measured on test ranges and actual speed achieved under combat conditions are entirely different creatures. The Merlin DEX-DX engines fitted to early production. Mosquitoes operated within strictly defined parameters: 14 pounds per square inch boost pressure for takeoff sequences, reduced settings for sustained cruising flight. These operational limits weren't arbitrary restrictions dreamed up by cautious bureaucrats. Rolls-Royce engineers had meticulously calculated detonation margins, bearing temperature thresholds, and piston crown stress tolerances through extensive testing. Push beyond these carefully established specifications, and you risked catastrophic mechanical failure. Shattered connecting rods punching through engine blocks, melted piston crowns turning into liquid metal, engines literally tearing themselves apart at 20,000 feet over enemy territory. The technical manuals couldn't have been clearer or more explicit. These operational limits were sacred. They were inviolable. They represented the boundary between safe operation and mechanical suicide. Yet by late 1942, as Mosquito squadrons began executing increasingly ambitious deep penetration reconnaissance missions into the heart of Germany, flight crews started reporting a disturbing and dangerous pattern. Yes, their aircraft were fast by any conventional measure. But increasingly, they weren't quite fast enough to guarantee survival. The Luftwaffe's Focke-Wulf 190 and the latest Messerschmitt 109G variants were systematically narrowing the performance gap. Interceptions were becoming uncomfortably commonplace rather than rare exceptions. A Mosquito caught over the Ruhr Valley might still escape its pursuer through pilot skill and aircraft performance, but the safety margin was evaporating with each passing month. The technological advantage was slipping away. Pilots returned from missions with increasingly harrowing accounts that painted a troubling picture. Tracer fire passing mere feet from their aircraft. Desperate dives that barely opened sufficient separation from pursuing fighters. Engines howling at maximum emergency power that somehow still wasn't quite adequate when a determined German pilot pressed his attack. The mathematics of pursuit geometry were unforgiving, and they were gradually shifting against the Mosquito crews. The Mosquito had brilliantly validated Geoffrey de Havilland's revolutionary vision. The wooden wonder had proven its worth in combat, but it desperately needed something additional, something the original designers hadn't anticipated, and the official technical manuals explicitly forbade. It required someone willing to examine engineering specifications, not as absolute limits carved in stone, but as conservative suggestions open to interpretation. Someone who understood that regulations written during peacetime might prove dangerously inadequate when confronted with war's brutal mathematical reality. Someone who could read between the lines of engineering tolerance and see not limitations but possibilities. Roderick Banks wasn't supposed to change anything. He wasn't supposed to innovate. He certainly wasn't supposed to revolutionize engine performance. He was classified officially as a fitter, not an engineer. A distinction the Royal Air Force's rigidly hierarchical structure took extremely seriously in 1942. His workspace at RAF Marham in Norfolk was one of countless similar facilities scattered throughout Bomber Command, servicing the Merlin engines that powered Lancasters, Halifaxes, and the rapidly expanding Mosquito fleet. His official responsibility was straightforward execution of established procedures, never innovation or experimentation. Strip engines according to manual specifications, inspect components against documented tolerances, replace worn parts with approved replacements, reassemble according to technical specifications, sign the logbook confirming completion, send the aircraft back to operational service. The entire maintenance system functioned smoothly because men like Banks followed instructions with absolute precision. The system depended on conformity, on predictability, on everyone doing exactly what the manuals specified without deviation or creative interpretation. Except Banks possessed an unusual characteristic that set him apart. He consumed technical documentation obsessively, voraciously, compulsively. Not merely the standard maintenance manuals that every fitter received, but the dense engineering specifications that Rolls-Royce included with engine deliveries, technical documents most fitters never even glanced at, dismissing them as unnecessarily complex. These documents were filled with thermodynamic calculations, metallurgical data tables, stress analysis charts, and engineering mathematics that seemed irrelevant to the practical work of maintaining engines. Banks studied these documents during meal breaks, tracing the mathematical logic underlying boost pressure limitations and fuel mixture ratios, trying to understand not just what the specifications required, but why they required it. He'd begun his career at Rolls-Royce's Derby factory as an apprentice in 1935, spending 4 formative years observing Merlin development firsthand before the RAF recruited him for wartime service as manufacturing capacity expanded. Those 4 years gave him insight into these engines at a depth unusual for someone wearing sergeant's stripes rather than an officer's insignia. He understood these power plants not as mysterious black boxes to be serviced according to checklist, but as comprehensible systems governed by physics and engineering principles. What Banks discovered in early 1943 was a fascinating inconsistency that made him question everything he'd been taught. The Merlin operational manual specified maximum allowable boost pressures in clear, unambiguous terms. But the underlying engineering documentation, the dense technical specifications he'd studied so carefully, revealed that the physical components could theoretically withstand significantly more mechanical and thermal stress. Not dramatically more, perhaps, but enough to matter substantially in combat situations where every additional mile per hour could mean the difference between life and death. The operational limit wasn't actually about the physical capabilities of forged steel crankshafts and aluminum alloy pistons. It represented what Rolls-Royce could confidently guarantee across thousands of engines operating in wildly varying conditions worldwide. Different climates, different fuel qualities, different maintenance standards, different pilot techniques. It was a built-in safety buffer designed to accommodate imperfect real-world conditions. Banks began contemplating a dangerous question that would have gotten him court-martialed if he'd voiced it to the wrong person. What would happen if you deliberately reduced that safety margin? Just slightly, just enough to matter, on engines you knew with absolute certainty were maintained in perfect condition. The mathematics proved seductive and compelling. Merlin power output correlated directly with manifold pressure, the boost pressure forcing the air-fuel mixture into combustion cylinders. Increase boost by merely 2 pounds per square inch, and you gained approximately 100 additional horsepower per engine. On a Mosquito equipped with twin Merlins that translated to perhaps 15 extra miles per hour at operational altitude. That might not sound dramatic on paper, but in combat geometry, it could easily represent the difference between successful evasion and a very abbreviated combat career. But beneath these appealingly simple numbers lurked significant complexity that could kill you if you got it wrong. Push excessive boost through an engine without proper safeguards, and detonation becomes inevitable. The fuel-air mixture exploding prematurely, rather than burning in controlled fashion, hammering pistons with shockwaves capable of shattering hardened metal components within seconds. The Merlin consumed 100-octane aviation fuel, which resisted detonation more effectively than lower grades through better chemical stability. But this protection wasn't unlimited or foolproof. Banks realized through careful study that the available safety margin depended entirely on precise fuel mixture control. Run excessively lean, too much air relative to fuel, and combustion cylinder temperatures would skyrocket dangerously. Run too rich, excess fuel relative to air, and you'd waste the performance advantage while fouling spark plugs with carbon deposits. The optimal setting existed within an extremely narrow band that varied dynamically with altitude, atmospheric pressure, throttle position, and engine temperature. Getting it wrong meant either wasting the modification's potential or destroying the engine spectacularly. Banks started cautiously and methodically, not recklessly. A single Merlin engine scheduled for routine overhaul became his experimental testbed and laboratory. He carefully adjusted the boost control unit, seemingly minor recalibration work that wouldn't attract immediate attention, advancing the overboost cutoff by 2 pounds per square inch. Then he slightly enriched the fuel mixture at high power settings, leveraging evaporative cooling as fuel vaporized inside cylinders to absorb excess heat that would otherwise stress aluminum pistons beyond their tolerance. On the workshop test stand, the engine screamed at boost pressures the Rolls-Royce technical manuals clearly classified as emergency only, meant to be sustained for seconds rather than minutes. Exhaust temperatures climbed measurably, but remained within acceptable parameters that wouldn't cause immediate component failure. Nothing fractured under the increased stress, nothing melted from excessive heat. The engine survived what the manual said it shouldn't survive. Having empirical evidence was one substantial challenge. Convincing anyone to install these modifications on an operational aircraft carrying living human beings proved entirely different and infinitely more difficult. RAF engineering officers lived in perpetual terror of unauthorized modifications to expensive government equipment. Every single alteration to aircraft systems required formal approval through bureaucratic channels that moved at glacial speed. Committees reviewing submissions from other committees, risk assessments filed in triplicate, technical documentation requiring multiple signatures, approval processes consuming weeks or months. Banks's modification existed in uncomfortable gray territory, not technically illegal under any specific regulation, but absolutely unsanctioned by any official authority. He desperately needed an advocate, someone willing to stake their professional reputation and potentially their career on a sergeant fitter's controversial intuition. He found that person in squadron leader Peter Channer, an experienced Mosquito pilot, who'd survived 3 complete combat tours and accumulated a healthy disrespect for official overcaution. Channer had flown a sortie over Cologne in February 1943 when a 109G had nearly caught him during the egress phase, closing within gun range, close enough that Channer could see the German pilot's oxygen mask through his canopy. That memory made him receptive when Banks explained what he'd discovered during a chance meeting at the maintenance hangar. Channer's response was pragmatically British. If it works, it's not illegal. It's initiative. If it fails, he paused meaningfully. Banks, you'll carry the blame entirely. They chose a Friday evening when the station engineering officer was conveniently away on administrative business. Banks and 2 trusted riggers he'd trained personally worked through the entire night, modifying the boost controls and fuel delivery system on Channer's assigned Mosquito, serial number DZ. By dawn, the aircraft sat on the dispersal hardstand, looking externally identical to every other Mosquito on the squadron. Only the maintenance logbook betrayed the truth, and Banks's entry was deliberately vague and innocuous. Fuel mixture optimization, routine adjustment. Nothing that would trigger immediate questions or investigation. The Merlin engine's boost control system was simpler mechanically than most people imagined, which made Banks's modifications both feasible to execute and potentially dangerous if done incorrectly. At its heart sat a barometric capsule, essentially a sealed metal bellows sensitive to atmospheric pressure changes. As aircraft climbed and ambient air pressure dropped, the capsule expanded mechanically, automatically adjusting the throttle's maximum allowable boost to prevent overstressing the engine in thin air at high altitude. Rolls-Royce had calibrated these capsules extremely conservatively, building in substantial safety margins that assumed pilots might abuse throttles during combat stress, that fuel quality might vary unpredictably between different batches, that maintenance standards might be imperfect under combat conditions. Banks's first intervention targeted exactly that conservative calibration. Inside the boost, control unit housing, a precision spring determined how much pressure the barometric capsule allowed, before automatically cutting power to prevent engine damage. By carefully selecting a slightly softer spring, not dramatically different, just fractionally more permissive, he shifted the maximum allowable boost from 18 pounds per square inch to 20. 2 pounds doesn't sound revolutionary when spoken aloud, but at 20,000 feet altitude, it meant the performance difference between 380 and 395 miles per hour. In pursuit geometry calculations, that 15-mile-per-hour gap could stretch from lethal gun range to safe separation distance in under 3 minutes of sustained flight. Those 3 minutes often meant the difference between survival and death. The fuel mixture adjustment demanded more delicate precision and deeper understanding. The Merlin's carburetor metered fuel flow through a complex series of jets, tiny brass orifices drilled to precise diameters measured in thousandths of an inch. Aircraft altitude and throttle position determined which specific jets supplied the combustion mixture at any given moment, and Rolls-Royce had sized them to run slightly lean under high power settings, prioritizing fuel economy and reducing the risk of fouling expensive spark plugs with excess carbon deposits from incomplete combustion. Banks recognized through careful analysis that this conservative approach compromised cooling effectiveness. When you're extracting maximum power from an engine, extra fuel doesn't just burn to produce power. It also evaporates inside cylinders before combustion, absorbing substantial heat through phase change that would otherwise stress aluminum pistons beyond their design limits. He addressed this cooling deficit by replacing the main fuel jet with one exactly 1 drill size larger, increasing fuel flow by approximately 8% at full throttle. Not enough to flood the engine with excess fuel or waste significant quantities, but sufficient to drop exhaust gas temperatures by 40 degrees Celsius at maximum power settings. That 40-degree temperature margin represented survival. Detonation and pre-ignition that destroyed engines catastrophically occurred when combustion cylinder temperatures exceeded specific critical thresholds. Banks was essentially buying thermal insurance against catastrophic failure. The magneto timing received careful attention too, though this modification involved greater risk. The Merlin fired its spark plugs before the piston reached the top of its compression stroke, giving the expanding flame front sufficient time to propagate completely through the compressed fuel-air mixture. Rolls-Royce specified 15 degrees before top dead center, a carefully calculated compromise between extracting maximum power and maintaining acceptable mechanical stress on engine components. Advancing the ignition timing to 18 degrees extracted measurably more energy from each combustion event through more complete burning, but substantially increased the mechanical stress transmitted through connecting rods to the crankshaft. Banks judged that the Merlin's bottom end, the massive crankcase and precision bearings, could handle this additional loading, provided the engine was maintained in absolutely perfect condition. Any engine showing even marginal wear, slightly worn bearings or cylinders that measured even slightly oval rather than perfectly circular, would fail catastrophically under the additional mechanical loading. This critical factor was precisely why Banks selected which engines received his modifications, with obsessive care bordering on paranoia. Any power plant showing even marginal wear indicators went back to standard factory specifications, without exception. Only Merlins fresh from complete overhaul, equipped with new pistons, bearings measured and verified to within 1,000th of an inch tolerance, and compression readings that tested identical across all 12 cylinders, received his treatment. He was deliberately pushing engineering boundaries, but he wasn't ignoring fundamental physics or gambling recklessly with lives. The modifications broke no specific written regulation, because existing regulations hadn't anticipated anyone attempting them. RAF maintenance doctrine assumed fitters would follow manufacturer specifications exactly without deviation. The official rulebook didn't explicitly say, "Thou shalt not adjust boost control calibration." It simply didn't conceive that anyone would try something so audacious without formal authorization. Banks operated skillfully in that silence between explicit permission and explicit prohibition, that uncomfortable gray space where genuine initiative lives alongside career-ending mistakes. Rolls-Royce's official position, had they known what was happening across multiple RAF stations, would have been unambiguous horror and immediate legal action. Their warranty explicitly voided if operating limits were exceeded under any circumstances. The company had systematically tested engines to complete destruction, meticulously determining operational limits by recording exactly when pistons melted into liquid aluminum, when bearings seized solid, when crankshafts twisted under excessive torque. These conservative margins existed because catastrophic mechanical failure at 20,000 feet altitude meant dead aircrew, and dead aircrew meant devastating liability, official investigations, destroyed corporate reputations, and potential criminal charges. But Rolls-Royce engineers weren't personally flying combat sorties over the Ruhr Valley with Focke-Wulf fighters queuing for firing solutions on their tails. Banks was betting his modifications on a calculated risk. That brief periods at elevated boost pressure, minutes rather than hours of continuous operation, wouldn't trigger the catastrophic failure modes that Rolls-Royce engineers rightfully feared. He was also betting on the superior detonation resistance of 100-octane aviation fuel, on his own demonstrated ability to select only the finest engines in perfect mechanical condition, and on riggers who'd monitor critical temperatures obsessively during flight testing. The morning after Banks completed modifying DZ-414, Peter Channer took the Mosquito up alone for initial testing. Standard test flight profile. Climb to 15,000 feet. Establish level flight at cruise power settings. Run through basic handling checks. Then came the critical moment of truth. Channer advanced both throttles smoothly to their stops and watched the boost pressure gauges climb steadily past the red warning line that marked official limits, needles settling at 20 pounds per square inch. The Merlin's characteristic sound deepened noticeably, transitioning from a steady roar to a harder, more urgent howl that vibrated through the entire airframe. The airspeed indicator unwound rapidly past numbers Channer had never witnessed in level flight before. The proof arrived dramatically over Gelsenkirchen on April 19, 1943. Squadron leader Channer's crew had been tasked with a hazardous daylight reconnaissance mission. Aerial photographs of synthetic oil production plants deep in the Ruhr Valley, exactly the sort of high-value target that invited aggressive attention from every Luftwaffe controller within radar range across western Germany. The Mosquito crossed the Dutch coast at 24,000 feet, cameras warming up to operating temperature. Channer's navigator calling out landmarks through the intercom with professional precision. Clear skies, perfect visibility, terrible conditions for staying unnoticed by enemy defenses. The German fighters appeared just 18 minutes into enemy airspace. Two Focke-Wulf 190s, twin-engine killers with devastating firepower, climbing hard from an airfield near Münster. Their powerful BMW radial engines clawed desperately for altitude, trying to reach interception position before the fast British bomber completed its mission and escaped. The Luftwaffe ground controllers' vectoring instructions were professionally executed and accurate. They'd positioned their fighters ahead of the Mosquito's projected track, cutting off the direct escape route back to the North Sea in safety. Channer spotted them at 6 miles distance, two dark specks silhouetted against cumulus clouds, turning aggressively to intercept. Standard Luftwaffe tactical doctrine, close from above and behind to maximize speed advantage from the dive, coordinate convergent fire from 20mm cannons and 13mm machine guns to create an inescapable killing zone. Channer didn't panic or deviate from his mission profile. He calmly completed the photographic run, allowing the reconnaissance equipment to capture its critically important images while the Focke-Wulfs systematically ate away the distance separating hunter from prey. Then, he spoke quietly to his navigator through the intercom. "Let's see what Banks gave us." The throttles were already positioned at maximum standard power, but now Channer deliberately activated the override mechanism, pushing them smoothly past the normal stops into territory. Rolls-Royce technical manuals clearly marked as emergency-only operation. The boost pressure gauges surged to 20 pounds, then fractionally beyond into previously forbidden territory. The Merlin engines responded with a snarl that vibrated through the entire airframe structure. The Mosquito accelerated like it had been physically kicked from behind. Channer felt the increase viscerally, not as gentle building of conventional acceleration, but something more immediate and violent. The airspeed indicator swept rapidly past 400 miles per hour, still climbing steadily. The pursuing Focke-Wulfs, already committed to their interception dive, suddenly found their carefully calculated geometry disintegrating. The Mosquito they'd expected to catch was inexplicably pulling away, opening the separation distance at a rate that shouldn't have been aerodynamically possible. The German pilots pushed their throttles harder, demanding everything their BMW engines could deliver, but physics and mathematics were unforgiving. At altitude, the Focke-Wulf 190's maximum sustainable speed was approximately 395 miles per hour. Channer's modified Mosquito was maintaining 415. 20 miles per hour advantage doesn't sound dramatic when spoken casually, but compounded across 10 minutes of pursuit, it translated to 3 miles of expanding separation, far beyond effective gun range. The German pilots fired optimistically at maximum range as their quarry steadily shrank into the distance, their cannon shells arcing uselessly through empty air. Channer's combat report, filed upon return to Marham, was characteristically understated and professional. Enemy fighters encountered, successful evasion through speed advantage, standard military prose that revealed nothing unusual to casual readers. What the dry official report didn't capture was the profound significance. This wasn't merely a lucky escape or clever tactical maneuvering by a skilled pilot. This was fundamental physics winning decisively. The Luftwaffe's premier interceptor, specifically designed and optimized to catch Allied bombers, had been comprehensively outrun in sustained level flight by an aircraft it should have destroyed easily. The performance gap shouldn't have existed according to all official specifications. Word spread through the Mosquito squadrons with the remarkable speed that only genuinely useful tactical information achieves in combat units. Other pilots began approaching Channer with careful, indirect questions, and Channer directed them discreetly towards Banks with a knowing look and minimal explanation. By May 1943, 3 additional Mosquitoes at Marham had received the modifications through quiet, unofficial channels. By June, Banks was spending his evenings working on engines from other squadrons, his modest workshop becoming an unofficial performance enhancement center. The modifications remained technically unsanctioned by any official authority, but they were increasingly tolerated by practical station commanders who cared more about returning their crews alive than achieving perfect regulatory compliance. The combat mission reports accumulated steadily through summer 1943, creating an undeniable pattern. On June 17th, a modified Mosquito successfully outran 3 Messerschmitt 100 known G6s over Hamburg during a photo reconnaissance mission. On July 3rd, another escaped a determined pursuit by Kurt Bühligen, a Luftwaffe ace with 112 confirmed victories, who knew precisely how to prosecute an interception with maximum efficiency. He couldn't catch the Mosquito despite perfect tactical positioning. On August 22nd, a crew limping home on a single functioning engine after devastating flak damage over Bremen used Banks's modifications on their remaining Merlin to stay ahead of 2 109s that should have finished them easily with overwhelming firepower advantage. The statistical evidence became completely undeniable to anyone examining the data objectively. Mosquitoes equipped with modified engines were consistently returning from combat sorties that conventional aircraft simply didn't survive. The combat loss rate for Banks' modified machines ran at less than half that of standard Mosquitoes, flying comparable high-risk missions into heavily defended German airspace. Survival bought precious time. Time bought irreplaceable combat experience. Experience bought measurably better bombing and reconnaissance results. The reinforcing circle was powerfully virtuous. Operation Jericho demanded precision that bordered on absolute suicide, a mission that shouldn't have succeeded under any rational analysis. The Amiens prison in northern France held approximately 120 members of the French resistance scheduled for execution by the Gestapo on February 19, 1944. London had received desperate messages through SOE intelligence networks: break the prison walls, give the prisoners a chance to scatter and escape, or they die. All of them. The mission required Mosquitoes to strike a 3-story building with 500-pound bombs, precisely breaching specific exterior walls without collapsing the entire structure onto the prisoners trapped inside. Low-level attack in broad daylight, penetrating 300 miles into occupied territory. Then the hazardous flight home through fully alerted German defenses. Group Captain Percy Pickard took operational command, personally assembling experienced crews from 140 Wing, battle-hardened men who'd flown to Oslo, Berlin, and targets even more optimistic than those. The mission planning consumed 4 intensive days. Detailed photographic reconnaissance revealed the prison's layout with remarkable precision. Outer walls, measured 2 feet thick of reinforced masonry. Guard barracks sat adjacent to the main building, German quarters that needed complete destroying, while French prisoner sections remained theoretically intact. The bombing would occur at rooftop height, perhaps 50 feet above ground level, which meant the explosive blast from your own weapons could potentially shatter your aircraft if timing wavered by even a second. 19 Mosquitoes lifted off from RAF Hunsdon on the morning of February 18th. The execution date had been moved forward unexpectedly, compressing preparation time dangerously. The formation flew at wave-top height across the English Channel, navigating by stopwatch and magnetic compass with no margin for error, arriving over Amiens at precisely 12:03 p.m. Pickard's aircraft led the first attack wave, 6 Mosquitoes climbing to 150 feet for their bomb runs. The 500-pounders struck with devastating precision, blowing substantial sections of the outer wall into scattered rubble, breaching the eastern wall near the condemned cells where resistance members awaited execution. The second wave targeted the guard quarters with equal precision, collapsing buildings and creating absolute chaos that prevented organized German response. The third wave circled overhead in reserve but wasn't ultimately needed for the attack. Intelligence reports confirmed later that 258 prisoners escaped successfully in the resulting confusion, including most of those scheduled for immediate execution by firing squad. But the successful bombing represented merely the first survival problem for the returning crews. The attack had occurred at midday with German radar stations fully alert across northern France. As the Mosquitoes regrouped for the return flight to England, Luftwaffe controllers scrambled every available fighter from airfields scattered between Amiens and the coastline. The British aircraft faced 40 agonizing minutes of exposure before reaching the relative safety of the English Channel, flying low over countryside where every road held Wehrmacht units equipped with radio communication to vector fighters onto targets. Pickard's Mosquito never made it home to debriefing. 2 Focke-Wulf 190s caught him near Beauvais, their synchronized guns finding the aircraft before evasive maneuvering was possible. Pickard and his navigator died instantly in the devastating gun strikes. 2 other Mosquitoes fell to aggressive fighters in those brutal minutes immediately following the attack, crews paying the ultimate price for flying straight and level during precision bomb runs that required absolute stability. The remaining 16 aircraft survived the gauntlet largely because of modifications Banks had now standardized across multiple squadrons. Squadron leader Ian McRitchie, leading the second attack wave, encountered 4 Focke-Wulf 190s climbing aggressively to intercept near Abbeville. His modified Merlin gave him the critical 10 miles per hour speed advantage that transformed potential lethal combat into a foot race he could win through superior sustained velocity. The German pilots fired optimistically at maximum gun range, their 20mm cannon rounds falling away progressively behind McRitchie's tailplane as the separation distance expanded beyond effective range. Flight Lieutenant Bob Iredale faced a more sustained and dangerous pursuit. A Messerschmitt 109 G6 bounced him from cloud cover south of Amiens. The German pilot executing a textbook interception attack that should have ended with Iredale's Mosquito scattering burning wreckage across a French agricultural field. Iredale slammed both throttles forward instinctively, feeling the engine note transform distinctively as boost pressure climbed into Banks's modified operating range. The 109 pilot stayed with him initially. The Gustav variant was genuinely formidable in level flight, theoretically capable of 390 miles per hour at low altitude. But capable of and sustained represent fundamentally different concepts in combat aviation. The Messerschmitt's Daimler-Benz engine was rated for specific power settings, and like the Merlin, exceeding them for extended periods invited catastrophic mechanical trauma. For 3 agonizing minutes, the two aircraft screamed across Picardy at absolute maximum power, the 109 holding position approximately 600 yards behind Iredale's tail, close enough to cause serious concern, too far to deliver killing fire effectively. Then slowly, incrementally, the separation gap began opening. Not dramatically like Channer's altitude interception. This wasn't decisive acceleration. At low level, air density robbed both aircraft of performance. But Iredale's Mosquito maintained 405 miles per hour, where the 109 could sustain only 395 without risking engine destruction. 10 miles per hour difference, compounding relentlessly across 3 minutes, became half a mile of life-saving separation. The German pilot fired a final desperate burst at impossible range and broke away sharply, probably cursing his diminishing fuel state. 12 of the returning Mosquitoes carried Banks's engine modifications. All 12 made it home safely. The 4 combat losses included Pickard's unmodified aircraft and 3 others flying to standard factory specifications. The sample size was admittedly small, the statistics not definitively conclusive by rigorous scientific standards, but surviving crews drew their own practical conclusions based on lived experience. By March 1944, Banks was receiving modification requests from squadrons he'd never heard of, engineering officers discreetly turning blind eyes to unauthorized changes they couldn't officially acknowledge without triggering investigations. Hermann Göring's rage was becoming legendary even by his notoriously theatrical standards. During a high-level meeting at Karenhall on March 8, 1944, he explosively interrupted a Luftwaffe technical briefing to demand, furiously, why German fighters couldn't catch wooden British furniture. The Reichsmarshal's frustration was entirely understandable from his perspective. Mosquitoes were appearing brazenly over Berlin in broad daylight, photographing the Chancellery and other sensitive government buildings, whilst Messerschmitt 109s scrambled uselessly thousands of feet below. The humiliation carried tactical, political, and deeply personal dimensions. Göring had personally promised Adolf Hitler complete air superiority over the Reich. Instead, plywood bombers mocked that promise daily at 400 miles per hour, untouchable by Germany's finest fighters. The Luftwaffe's increasingly desperate response revealed institutional panic, disguised as technical innovation. Messerschmitt and Focke-Wulf received urgent directives to extract additional speed from existing airframe designs through any means necessary. German engineers understood the fundamental problem's dimensions with painful clarity. The Mosquito, at operational altitude with a competent crew, represented a performance envelope their standard fighters couldn't quite reach in sustained pursuit. Close. Maddeningly close. But aviation doesn't award consolation points for near misses. Messerschmitt's attempted solution was the 109 G10 variant, introducing a Daimler-Benz DB605D engine with significantly improved supercharging and emergency boost capacity, raising output to 2,000 horsepower. On paper, the specifications appeared impressive. In harsh operational practice, the modifications added substantial weight that partially negated the raw power increase. The G10 could touch 426 miles per hour at optimal altitude, but only briefly, and only if the pilot accepted engine operational life measured in hours rather than days or weeks. German maintenance logistics couldn't possibly sustain such mechanical abuse across operational fighter squadrons. Focke-Wulf pursued the TR-152, Kurt Tank's obsessive refinement of his successful FOW-190 design. Longer wings for improved high-altitude performance, pressurized cockpit for pilot comfort, Junkers Jumo, 213 engine producing 2,050 horsepower with MW50 methanol water injection for emergency power. The prototypes achieved genuinely remarkable performance specifications: 472 miles per hour at 41,000 feet, altitude capability that should have dominated Mosquito operations decisively. But prototype performance and mass production are entirely different challenges. Development consumed precious time Germany simply didn't possess. The first TR-152s reached operational fighter units in January 1945, far too late and produced in far too few numbers to affect strategic outcomes meaningfully. The Luftwaffe also attempted directly mimicking Banks's approach. Unauthorized boost pressure increases on existing engines. Several fighter staffelen experimented with adjusting boost controls on DB605 and BMW 801 power plants, seeking the performance margin British pilots, apparently, enjoyed routinely. The results were absolutely catastrophic and immediately halted. German engines fundamentally lacked the Merlin's inherently robust construction and suffered from increasingly poor manufacturing quality, as relentless Allied strategic bombing systematically disrupted production facilities. Bearings failed prematurely, pistons cracked under thermal stress, connecting rods punched violently through crankcase walls. A Messerschmitt 1M19 disintegrating spectacularly over its own airfield because the desperate pilot demanded too much emergency power became a cautionary training film, demonstrating exactly what not to attempt under any circumstances. The fundamental problem transcended mere engineering principles. It was industrial capacity under sustained siege. Rolls-Royce's Derby and Crewe factories operated with consistently high material quality, stable skilled labor pools, and completely uninterrupted supply chains throughout the war. German aero engine production by 1944 involved increasingly dispersed facilities, staffed partially by slave labor of wildly varying skill levels, using substitute materials when proper specialized alloys became unavailable. Manufacturing tolerances suffered progressively. Quality control became largely theoretical rather than practical. An engine that measured correctly on paper and passed cursory inspection might conceal fatal metallurgical flaws that emerged catastrophically only under combat stress. Oberst Adolf Galland, General der Jagdflieger, and one of Germany's most experienced fighter leaders, understood this grim reality with bitter clarity. In a remarkably candid April 1944 memorandum to Göring, Galland noted that even when German fighters achieved successful initial interceptions of Mosquito formations, the bombers frequently escape through sustained high-speed flight that our aircraft cannot match without risking catastrophic mechanical failure. He formally requested permission to withdraw fighters from less strategically critical defensive areas to concentrate overwhelming numerical superiority against known Mosquito routes, accepting increased bomber losses elsewhere to guarantee kills against the fast reconnaissance aircraft. Göring rejected the proposal outright. The Reichsmarschall remained stubbornly convinced that technical solutions existed, that German engineering superiority, an unquestioned article of Nazi ideological faith, would inevitably produce aircraft to humble British plywood through superior design and manufacturing. He diverted increasingly scarce resources toward jet fighter development instead. The Messerschmitt Me 262 promised revolutionary speed that would render the Mosquito completely obsolete overnight. The jets did eventually fly operational missions, and they were indeed fast enough to catch anything the Allies fielded. But they arrived in handfuls when hundreds were desperately needed, piloted by hastily trained crews with minimal jet experience, burning scarce aviation fuel. Germany couldn't afford to spare for training or extended operations. Meanwhile, Mosquito operations intensified dramatically across all theaters. The fast bombers struck high-value targets in broad daylight that heavy four-engine bombers attacked only under protective darkness. Ball-bearing manufacturing plants at Schweinfurt, V-weapon launch sites scattered along the French coast, Gestapo headquarters in Copenhagen requiring surgical precision to avoid Danish civilian casualties. The cumulative psychological impact on German civilian morale exceeded even the substantial physical damage inflicted. German civilians watching mosquitoes streak overhead completely untouched by flak, or fighters understood with devastating clarity that their once vaunted Luftwaffe had irreversibly lost control of German airspace. Some Luftwaffe pilots developed grudging professional respect for their consistently elusive opponents. Hauptmann Heinz Baer, a decorated veteran with 33 confirmed aerial victories, wrote in his personal diary after yet another failed Mosquito interception. The Tommy flew like the devil himself was pursuing him. Or perhaps Baer didn't realize the devil was inside those British engines, hidden in modified boost controls and enriched fuel mixtures. Baer knew nothing about Sergeant Banks, about carefully adjusted springs and precisely enlarged fuel jets, but he recognized instinctively that something beyond excellent design office work gave those wooden bombers their seemingly impossible edge over Germany's finest fighters. By autumn 1944, Banks's modest workshop at Marham had evolved into something between underground legend and logistical necessity. Crews arriving from distant stations brought bottles of scarce whiskey and complex engineering problems, hoping the sergeant with the apparently magic touch might examine their troublesome Merlins. Banks obliged when operational tempo permitted, but demand vastly outstripped what one man could physically achieve working 18-hour days. The practical solution emerged organically through necessity. He began systematically training others, carefully passing specialized knowledge to fitters who demonstrated both genuine technical aptitude and appropriate operational discretion. The informal network expanded carefully and deliberately. Banks identified promising candidates through personal recommendation only, preferring mechanics who'd previously worked at Rolls-Royce manufacturing facilities or demonstrated unusual initiative-solving maintenance problems. He'd invite selected candidates to observe an engine modification session, explaining the underlying thermodynamic theory, whilst his experienced hands performed the delicate practical work: the boost control adjustment, the fuel jet replacement, the magneto timing advance. Each critical procedure was demonstrated twice completely. Then the student attempted it under close supervision with Banks, watching every move. He immediately rejected anyone who couldn't clearly articulate why each modification worked at a fundamental level, not merely how to execute it mechanically. Deep understanding prevented catastrophic mistakes born from superficial knowledge. Flight Sergeant Thomas Yardley became Banks's most accomplished and trusted student. Yardley had spent 3 valuable years at Rolls-Royce's Hillington factory near Glasgow, before joining the RAF when war production expanded, and he possessed an intuitive grasp of practical thermodynamics that Banks recognized immediately. By November 1944, Yardley was independently modifying engines at RAF Coningsby, serving Lancaster heavy bomber squadrons that were beginning to receive Merlin-powered variants. The modifications transferred successfully to the heavy 4-engine bombers, though performance gains were inevitably less dramatic than on lighter Mosquitoes. A fully loaded Lancaster couldn't outrun determined fighters regardless of engine improvements, but the additional power measurably improved climb rates and maximum altitude ceiling, making them marginally harder targets for flak batteries and fighters to engage effectively. Corporal James Dennison established another capability node at RAF Wattisham in Suffolk, focusing exclusively on Mosquito squadrons operating tactical reconnaissance and precision strike missions. Dennison was considerably younger than Banks, only 23 years old, but he'd absorbed the technical lessons thoroughly and added his own innovations. His particular contribution was refining fuel mixture adjustments for different specific operational profiles. Mosquitoes flying dangerous low-level anti-shipping strikes against German coastal convoys needed substantially different mixture settings than those conducting high-altitude strategic reconnaissance deep over Germany. Dennison systematically worked out the optimal variations, creating what amounted to mission-specific engine configurations. The expanding unofficial network operated through carefully controlled information security. Modifications were never discussed over telephone lines or mentioned in official written correspondence that could be intercepted or filed. Specialized knowledge passed exclusively face-to-face, mechanic to trusted mechanic, usually during station visits that officially concerned only routine maintenance coordination matters. Squadron engineering officers developed comfortable, plausible deniability as protective cover. They knew intuitively that something significant was happening to improve engine performance beyond normal specifications, but official paperwork showed only standard overhauls and routine adjustments. If questioned by higher authority during inspections, they could honestly claim complete ignorance of technical specifics. This pragmatic arrangement suited everyone's interests except rigid adherence to regulations. Air Ministry engineering directives, still explicitly, required all aircraft modifications to receive formal approval, extensive testing, and complete documentation before implementation. Banks's expanding network violated that bureaucratic structure entirely, operating as an effective shadow system, optimizing combat aircraft through informal channels. Bureaucracy didn't officially acknowledge or control. The situation remained sustainable only because operational results overwhelmed regulatory objections. Mosquito squadrons with access to modified engines consistently showed measurably better operational statistics, higher sortie completion rates, dramatically lower combat losses, more successful target engagements. The numbers spoke for themselves to anyone examining mission reports objectively. Yet the modifications carried genuine risks that Banks never downplayed or concealed from crews. Engines operating routinely at elevated boost pressures accumulated metal fatigue substantially faster than standard power plants. Critical components that might normally survive 200 hours between major overhauls sometimes required replacement at 150 hours or less. Piston crown erosion occurred more frequently. Exhaust valves showed measurably increased wear. The enhanced performance came with a tangible maintenance cost that someone ultimately had to pay. More seriously, catastrophic mechanical failures did occur with disturbing regularity. In December 1944, a Mosquito taking off from RAF Banff suffered a catastrophic connecting rod failure in the port engine at merely 400 feet altitude. The fractured rod punched violently through the crankcase wall, instantly severing oil lines and destroying the engine mount. The aircraft crashed into the Moray Firth, killing both crew members before rescue vessels could respond. The subsequent investigation traced the failure directly to excessive boost pressure operation on an engine that post-crash examination revealed had microscopic stress cracks in the connecting rod. Invisible flaws that standard inspection procedures hadn't detected, but Banks's higher operating stresses had catastrophically propagated. In February 1945, Flight Lieutenant David Wilson experienced every pilot's nightmare scenario over the North Sea. His starboard engine seized completely without warning during return from a reconnaissance mission over Kiel. The engine hadn't failed gradually with declining oil pressure or rising temperatures. It simply stopped instantly, the propeller windmilling uselessly. Wilson managed to ditch successfully in heavy seas, and both crew members survived in their dinghy until air-sea rescue located them 4 hours later, suffering severe hypothermia. The engine teardown revealed catastrophic exhaust valve failure. A piece of the valve face had fractured under thermal stress, fallen into the combustion cylinder, and hammered the piston crown into sharp-edged fragments. Those metal fragments destroyed the cylinder wall, contaminated lubricating oil with abrasive particles, and the resulting metallic slurry systematically destroyed the main bearings within minutes. Banks read the detailed investigation report with the grim expression of someone watching a predicted disaster finally materialize. He'd known intellectually from the beginning that sustained high-power operation stressed components far beyond their original design life expectations. The question haunting him had always been whether the undeniable tactical advantage justified the measurable mechanical price. Wilson's near-death experience provided an uncomfortable, concrete answer he couldn't ignore or rationalize away. The brutal mathematics of acceptable loss were emotionally difficult, but operationally unavoidable. Between June 1944 and March 1945, Mosquitoes equipped with modified engines flew approximately 3,400 dangerous operational sorties deep into defended German airspace. Combat losses totaled 11 aircraft destroyed by enemy action, a loss rate of 0.32%. Standard specification, Mosquitoes flying statistically comparable high-risk missions lost 47 aircraft from 6,800 sorties, 0.69% loss rate. The modified aircraft were statistically twice as likely to return safely from combat, but those same modified engines suffered 23 mechanical failures severe enough to force emergency landings or aircraft abandonments. 3 crews died in crashes directly attributable to engine mechanical failure rather than enemy action. Another 7 suffered serious injuries requiring hospitalization and medical evacuation. The moral arithmetic troubled Banks more deeply than he ever admitted to colleagues. Each modification he personally approved might save a crew from German fighters through superior performance, but simultaneously placed them at measurable risk from their own power plant's enhanced but less reliable operation. The decision wasn't his alone to make. Pilots explicitly requested the modifications after careful briefing, understanding the complex trade-offs involved. But Banks still felt the profound weight of personal consequences. When an engine failed catastrophically, he knew his own hands had adjusted those boost controls, selected that specific fuel jet, advanced that magneto timing. The responsibility was inescapable. Squadron engineering officers faced fundamentally similar moral calculations. They could maintain engines to conservative peacetime standards, accepting the resulting performance penalty and potentially higher combat losses. Or they could aggressively push boundaries and accept occasional catastrophic mechanical failures. Most pragmatically chose the latter approach, reasoning that combat killed with far greater statistical efficiency than mechanical unreliability. A crew shot down over Germany faced either immediate death or years in brutal prison camps. A crew forced to ditch from engine failure usually survived if air-sea rescue services responded quickly. The North Sea was harsh and unforgiving, certainly, but it wasn't the Gestapo. Rolls-Royce officially remained studiously oblivious to the widespread field modifications, but company engineers weren't stupid or blind. Field service representatives visiting RAF operational stations routinely noticed engines return for major overhaul, showing distinctive wear patterns completely inconsistent with rated operating conditions. Careful questions were asked. Deliberately vague, non-committal answers were provided by squadron personnel. The representatives dutifully reported their technical suspicions to Derby headquarters, where senior management faced an uncomfortable strategic reality. Their precision-engineered Merlin engines were clearly being operated significantly beyond official specifications, apparently quite successfully, and officially complaining might force the RAF to stop the practice entirely, potentially reducing the Mosquito's demonstrated combat effectiveness. Some Rolls-Royce engineers were privately fascinated rather than horrified by the implications. The company had been deliberately conservative with the Merlin's operational ratings, sensibly prioritizing long-term reliability over extracting maximum possible performance. But they'd always suspected intellectually that additional performance margin existed beyond conservative ratings. Banks's unauthorized modifications were essentially functioning as an unsanctioned, but remarkably comprehensive field test program, providing invaluable operational data that peacetime testing protocols would never generate. These were engines systematically run to complete destruction under actual combat conditions, accumulating thousands of operational hours under maximum stress, all meticulously documented in squadron maintenance logs. The human cost extended well beyond crash crews and investigation reports. Ground crew personnel working on modified engines operated under relentless psychological pressure that gradually accumulated. They knew intellectually that each critical decision, approving a specific engine for operational flight, deliberately delaying a scheduled overhaul by 10 hours to complete an urgent mission, accepting a marginally elevated temperature reading, carried genuine life-or-death consequences for air crews they knew personally. Flight Sergeant Yardley developed a bleeding stomach ulcer by early 1945, the accumulated stress of responsibility manifesting in painful, physical symptoms. Several experienced fitters requested transfers to non-operational maintenance units, finding themselves psychologically unable to sustain the constant burden of knowing their technical decisions directly affected survival. Banks himself visibly showed the accumulated strain. Photographs from late 1944 reveal a man who'd aged dramatically in just 2 years of intense pressure. The confident young mechanic who'd first modified DZ-414 in spring 1943 had transformed into someone who understood intimately that innovation killed people as well as saved them. He still believed firmly the modifications remained operationally necessary. Combat statistics overwhelmingly supported that rational conclusion. But statistical necessity didn't eliminate personal guilt when things went catastrophically wrong. The question of whether to continue the modification program became effectively moot in February 1945, when Rolls-Royce's chief engineer arrived at Marham completely unannounced. Ernest Hives deliberately didn't announce his visit because he wanted to observe actual reality, not a carefully sanitized version prepared for management inspection. The managing director of Rolls-Royce's critical aero engine division arrived at RAF Marham on February 12, 1945, driving himself in a staff car borrowed from the Air Ministry to avoid advance notice. He found Banks in workshop number 3, both arms buried to the elbows in a partially disassembled Merlin that had accumulated 147 operational hours since its last modification cycle. Hives watched in complete silence for 10 minutes before speaking. "Show me everything you're doing, Sergeant, all of it. Don't leave anything out." The intense conversation that followed lasted 3 exhausting hours. Banks systematically explained the boost control modifications in complete technical detail, physically demonstrated the precise fuel jet replacements, walked Hives step by step through his complex decision matrix for selecting which specific engines received modification treatment. He didn't apologize defensively or attempt to justify his actions. He simply presented the technical reality objectively and the supporting combat results. Hives asked precisely targeted questions about detonation margins, bearing load calculations, and thermal stress distribution. This wasn't an adversarial interrogation. It was 2 highly skilled engineers discussing complex problems that most people couldn't begin to comprehend, speaking a shared technical language. Hives had brought detailed service records for 200 Merlin engines randomly selected from operational squadrons across Bomber Command. He methodically spread them across a workshop workbench, systematically sorting modified from standard power plants based on distinctive wear patterns clearly visible in the maintenance documentation. The modified engines showed measurably higher component wear exactly as Banks had predicted from theory, but actual failure rates remained within operationally acceptable bounds provided maintenance discipline stayed rigorous and uncompromising. What genuinely surprised Hives was the remarkable consistency across units. Banks's modifications weren't random experimental tinkering by an enthusiastic amateur. They represented a coherent, systematic engineering approach applied with remarkable discipline and consistency. The Rolls-Royce director asked directly about failures. Banks provided his personal notebook, a simple log meticulously tracking every modified engine. 23 mechanical failures across 3,400 operational sorties, a failure rate of 0.68%. Hives silently compared this against the standard Merlin's peacetime operational failure rate of 0.31%. The modified engines failed twice as frequently, but aircraft equipped with them survived combat encounters at twice the rate of standard aircraft. The net statistical effect was fewer dead aircrew overall, from a purely utilitarian perspective, stripped of sentiment. Banks's controversial modifications saved lives in aggregate. Hives's response surprised everyone present in the workshop that February afternoon. Rather than ordering the unauthorized modifications immediately stopped and threatening disciplinary action, he thanked Banks sincerely for identifying performance margins that Rolls-Royce had been excessively conservative to exploit fully. The company had indeed built substantial safety factors into the Merlin's operational ratings to accommodate variable conditions, and extended combat operations had conclusively revealed those margins were considerably larger than strictly necessary under controlled conditions. Banks hadn't discovered anything Rolls-Royce engineers didn't theoretically understand. He'd simply been willing to act decisively on that knowledge without waiting for lengthy committee approval processes that might take years. Within weeks of Hives's visit, Rolls-Royce issued Technical Service Bulletin 184, dated March 7, 1945. The official document formally authorized increased boost pressures for Merlin engines in specific military applications, essentially codifying Banks's field modifications with explicit official sanction. The technical bulletin specified strict conditions. Engines must be fresh from complete overhaul, operating exclusively on verified 100-octane aviation fuel, with mandatory detailed inspections at 150-hour intervals. The enriched fuel mixture became standard specification for high-power settings. Magneto timing recommendations remained unchanged at conservative settings. Rolls-Royce engineers judged the crankshaft stress increase excessive for general application, though they didn't explicitly prohibit it. The bulletin instantaneously transformed Banks's controversial gray market modifications into approved standard procedure. What had been technically illegal for 2 years became officially sanctioned overnight, retroactively justifying 2 years of unauthorized field engineering. More significantly, from Banks's perspective, it vindicated his technical judgment completely. Rolls-Royce wasn't merely tolerating his work or overlooking regulatory violations, they were explicitly adopting it as improved standard practice. The measurable impact extended far beyond Mosquito squadrons. Merlin engines powering late-model Spitfires and American P-51 Mustangs received similar performance modifications, measurably improving high-altitude combat effectiveness against Germany's emerging jet fighters. The Merlin 100 series engines developed specifically for post-war civil and military applications directly incorporated lessons learned from wartime field modifications, including substantially improved detonation resistance and higher sustainable boost pressures. Banks's fingerprints were invisibly but indelibly present throughout the Merlin's final evolutionary development, though his name appeared nowhere in official development documentation. Recognition arrived in characteristically understated British military fashion. Banks received promotion to warrant officer in April 1945, highly unusual for someone completely lacking aircrew flying qualifications or officer status. The official citation mentioned exceptional technical contributions to operational effectiveness, deliberately vague bureaucratic language that entirely concealed the actual achievement's magnitude. Several pilots whose lives had been directly saved by modified engines wrote personal letters of gratitude, though most simply sought Banks out during station visits, shook his hand firmly, and said nothing more than a quiet, "Thank you." The best possible gratitude was simply coming home alive to their families. After Germany's unconditional surrender in May 1945, Rolls-Royce offered Banks a permanent civilian position at their prestigious Derby facility, a responsible role in experimental engine development, where his demonstrated willingness to push boundaries intelligently would be considered a valuable asset rather than dangerous liability. He accepted the offer, leaving the RAF in September 1945 with a service record describing him merely as competent and reliable, damning with faint praise that entirely missed the point of his extraordinary contribution. Banks spent the next 47 productive years refining engines for Rolls-Royce, his wartime innovations gradually absorbed into mainstream engineering practice without public fanfare or recognition. The company's post-war Merlin developments incorporated numerous lessons learned from wartime field modifications, improved detonation resistance through better fuel injection, higher sustainable boost pressures, enhanced thermal management systems. Banks's influence quietly permeated the Merlin's final evolution, though his name appeared nowhere in official development records or patent applications. He died peacefully in 1992, age 76, in suburban Derby. His obituary in the local Derby Telegraph mentioned a distinguished career in aerospace engineering spanning nearly 5 decades, but said absolutely nothing about mosquitoes, wartime modifications, or lives saved. The complete story might have vanished entirely from historical record except for a chance conversation at a 1995 Mosquito aircrew reunion, where 3 independent veterans casually mentioned Banks's engines in separate conversations, and a curious aviation historian finally asked what that intriguing phrase actually meant. The full account emerged gradually over subsequent years, painstakingly pieced together from scattered maintenance logs, squadron operational records, and recorded interviews with surviving ground crew members. What became abundantly evident through this research was that Banks had achieved something genuinely rare in military institutional history: meaningful, tactical innovation originating from below the officer ranks. A non-commissioned sergeant identifying critical performance margins that university-educated engineers and senior officers had either completely missed or feared to exploit without authorization. His success revealed profoundly uncomfortable truths about institutional engineering conservatism. Rolls-Royce's substantial safety margins, while entirely prudent and appropriate for general application across thousands of engines operating in wildly variable global conditions, proved demonstrably excessive for engines maintained to the highest possible standards and operated by highly trained crews in specific controlled circumstances. Banks recognized the crucial distinction that safe for all possible conditions wasn't identical to optimal for particular conditions. The Merlin could reliably sustain significantly enhanced performance provided you rigorously controlled all critical variables: perfect maintenance, consistent fuel quality, obsessive monitoring during operation. The manufacturer's blanket conservative restrictions prevented accessing genuine performance that was legitimately available under properly controlled conditions. This fundamental insight carries direct relevance to modern aviation engineering. Contemporary aircraft engines routinely operate under similarly conservative official ratings, with manufacturers protecting themselves from potential liability while accommodating highly variable operational conditions worldwide. Military and commercial operators routinely discover through experience that engines can reliably deliver substantially more than certified specifications suggest under optimal conditions. But safely exploiting that hidden margin requires exactly what Banks demonstrated with such remarkable effectiveness: deep technical knowledge extending beyond mere procedural compliance, obsessive quality control at every stage, and calculated willingness to accept accelerated component wear in direct exchange for enhanced performance when operationally necessary. The controversial modifications also illustrated the fundamental philosophical difference between engineering for peacetime and engineering for war. Peacetime priorities sensibly emphasize component longevity, cost-effectiveness, and substantial safety margins that comfortably accommodate imperfect maintenance under less than ideal conditions. War ruthlessly prioritizes immediate survival above all else, rationally accepting significantly reduced component operational life if it keeps trained crews alive today, regardless of tomorrow's maintenance, bills, or replacement costs. Banks understood intuitively that an engine surviving only 150 operational hours instead of the specified 200 was entirely acceptable if those 150 hours prevented a highly trained crew from dying over Berlin. Modern military aviation continues grappling with this fundamental tension daily. 4th and 5th generation fighters have official conservative performance limitations and unofficial emergency combat limitations that experienced pilots routinely employ when immediate survival demands it. The F-15's engines, for example, have standard thrust ratings for normal operations and substantially higher emergency ratings that dramatically shorten engine operational life but provide absolutely crucial performance advantage when necessary for survival. Banks pioneered this pragmatic doctrine for his generation establishing the enduring principle that immediate survival conclusively justifies accepting accelerated wear. The Mosquito's exceptional post-war reputation benefited enormously from performance modifications it routinely carried during intensive combat operations. Performance figures cited in authoritative aviation histories often reflected Banks' modified aircraft, rather than original factory specifications. The Mosquito achieved legendary iconic status partly because Banks made it measurably faster than Geoffrey de Havilland's brilliant original design specifications intended. This creates fascinating historical irony. The aircraft's iconic speed that made it legendary resulted substantially from unauthorized field modifications that technically violated virtually every regulation governing proper aircraft maintenance procedures. Engineering education programs occasionally examine Banks's work as an illuminating case study in practical problem-solving versus institutional procedure and bureaucratic control. His controversial modifications demonstrated technically sound engineering reasoning, systematically applied entirely outside official authorization channels, raising uncomfortable questions about when established rules should be followed absolutely and when they should be intelligently challenged based on circumstances. There's no universally comfortable answer. Banks proved correct. His modifications measurably saved hundreds of lives. But had he been wrong, had engines failed catastrophically at dramatically higher rates, he would certainly have been court-martialed for reckless endangerment. The broader lesson concerns innovation's true source within large organizations. Transformative improvements frequently originate from genuinely unexpected place, not prestigious design offices staffed with PhDs or well-funded research departments, but frontline operational workshops where people directly confronting urgent problems develop practical solutions completely unconstrained by institutional thinking or bureaucratic procedure. Banks wasn't inherently more intelligent than Rolls-Royce's brilliant engineers. He was simply differently positioned within the system, facing radically different operational incentives, and willing to accept calculated risks that company engineers couldn't possibly justify professionally or legally. His modest workshop at Marham was demolished during station modernization in 1962. Nothing whatsoever marks the precise location where Banks first modified DZ-414 or trained the dedicated fitters who systematically disseminated his revolutionary techniques across dozens of squadrons. The specific Mosquito that carried his modifications to the legendary Operation Jericho survived the war intact, only to be unceremoniously scrapped in 1947 during post-war demobilization. Its historically significant engines melted down for basic aluminum scrap value. Physical evidence systematically disappeared, leaving only fragmentary documentation and rapidly fading memories. Yet Banks's profound influence unmistakably persists in ways he never personally witnessed or imagined. Modern engine development programs incorporate sophisticated field feedback mechanisms specifically designed to systematically capture exactly the type of operational insights he generated through practical experience. Operators routinely reporting unexpected performance margins, engineers professionally investigating unauthorized field modifications rather than automatically prohibiting them. Rolls-Royce's corporate successor companies maintain formal organizational channels for field service representatives to systematically report unusual but demonstrably successful operational practices, deliberately institutionalizing what Banks accomplished informally through personal relationships. The Mosquito's enduring legend persists because it succeeded spectacularly at combat missions everyone initially insisted were operationally impossible. It flew repeatedly to Berlin and returned safely. It bombed Gestapo headquarters with surgical precision. It consistently outran the Luftwaffe's absolute finest fighters throughout 6 brutal years of total warfare. That remarkable success certainly rested substantially on Geoffrey de Havilland's brilliant original design vision and aerodynamic excellence. But it also depended critically on a working-class mechanic who obsessively read the technical manuals, thoroughly understood the engineering margins, and courageously decided that saving aircrew lives absolutely justified intelligently bending rules that nobody even realized could be bent.